All right, now an example of a vector field that we've actually already seen back in chapter 13 is the gradient of a function. So if I have a function f of two variables and I compute its gradient at a point xy, then the output is a vector whose I component is the x derivative of f evaluated at xy, and whose j component is the y derivative of f evaluated at xy. So the input is a point in the plane, and the output is a two-dimensional vector. So this gradient operation defines a vector field. And now if you have a vector field capital F and it's equal to the gradient of some function little f, then capital F is called the gradient field for little f, and little f we're going to call a potential function for the field capital F. And for those of you that have taken some physics, you might wonder if this is related to something like potential energy, and the answer there is yes, and we will look at potential functions and some of their applications in more detail later in the chapter. All right, so now we know that the gradient points in the direction of max increase for the function f. So if I have some level curves for the function f, like maybe these describe the altitude of a canyon. And we're at the bottom of the canyon and we want to book out of there as fast as possible, then we should head in the direction of max ascent, right? We should head in the direction of the gradient. Okay, what we also know about the gradient is that if I'm at a point, say xy, and I draw the level curve of f through that point, then the gradient evaluated at xy is perpendicular to this level curve. Okay, so if I go ahead and sketch the gradient field, I'm going to see a bunch of vectors like this, right? You can see that they are all perpendicular to these level curves at these points of contact. Okay, so in the next problem, question 3, we're going to see some illustrations of gradient fields, and I will see you there. All right, thanks.